first of all, many congratulations for the festival of Dashera. I hope you all are doing good. Your family is safe and healthy. So please enjoy the festival in the most best possible manner. Okay, so let's start the discussion for the topic. So basically, in this particular session, I'm going to discuss 4 most important questions of ALU, data path and control unit. So guys, from this particular topic, the questions are asked very rarely. If a question is asked, then it can be only of 3 or 4 types. Given a data path, they will ask you that how many cycles will be required in order to execute particular instruction. That's one type. Another is, they may ask you that what will be the size of control word with respect to horizontally microprogram control unit or vertically microprogram control unit. Apart from that, they may ask you the sum of product expression for the control signals in hardwired control unit. So these are 3 basic types of questions. Apart from that, some other type of questions may also be framed, but these are the 3 basic types of questions which can be asked from this particular topic, right? So let's start. This is brief introduction of myself. My name is Vishal Rawatia. I have 10 plus years of teaching experience. Following are the achievements and areas of expertise. Okay. Now, this is my Telegram group. If you guys have any doubt related to computer science preparation, gate preparation of computer science or DA paper, then you can ask me at this particular Telegram group and I'll be happy to answer. Now, okay, so there are some announcements. BYJU'S exam prep team is going to conduct a national scholarship test on 29th of October. Do participate in this test. If you perform good, then you may avail up to 90% off on all the programs which are being offered by BYJU'S exam prep. Apart from that, Richa Gupta ma'am is going to conduct a workshop for GATE 2025 aspirants. If you want to know that what will be the detailed preparation strategy, that how you can ace the GATE 2025 exam, then this workshop is for you. This will be conducted on 24th of October, that is tomorrow at 7:30 p.m. So for both of them, you just need to install the application BYJU'S exam prep app and you just need to register using your mobile number. Okay. Apart from that, the most important thing, if you are GATE 2024 aspirant, then mega mock tests are being conducted by BYJU'S exam prep. Please participate in this mega mock test. See, this is very important. This is a very crucial time when you need to learn that how to manage the time when you are sitting in the examination hall. This is not a one-day target that you will do something and next day you will be saving a lot of time and you will know that what all needs to be done. Eventually, you will ace on this particular thing also. So keep participating in the test series so that you will know that how you can utilize those 3 hours in the most efficient manner. So for computer science student, the next test will be conducted on 28th of October at 12 p.m. right? So do participate in this. This will be eventually the test on programming and data structure, algorithms and operating system. It will be a full-length question, full-length test, like I mean not the full length in terms of all the subject, but it will consist of 65 questions and the duration of the test will be 3 hours and the maximum number of marks will be 100 marks. Okay. So please, sorry guys. Okay, so there is a link in the description to download the application. You can download the application from the link provided in the description and register yourself using your mobile number, and you guys can get all the benefits which are being offered by the BYJU'S exam prep. This 2 more announcement for GATE 2024 aspirants. The crash course is going on. You guys can enroll for this crash course. This is for the purpose of revision, and if you just want to revise or if you just want to brush up all the topics of all the subjects, then this course is for you. You guys can enroll for this. Apart from that, the courses have also been launched for GATE 2025 and GATE 2026. You can enroll for them also. Now the number, if you want to enroll, then these are the numbers which you can use for enrolling in those particular courses. Okay guys, so this is the question number 1. So the questions are comparatively lengthy from this particular topic, therefore I have separated the questions and diagrams for those questions on two different slides. Please bear with that. Okay, so consider the following data path. So this is your data path. This is your data path. Please try to understand what is happening here. This is your ALU, right? This is your memory data register. If you want to perform, if you want to transfer any data to the memory, or if you want to receive any data from memory, then it will come from, or it will pass via memory data register. If you want to perform any memory operation, then the address will be provided to memory controller via memory address register, right? So these are the things. So these two are used for memory operations. Apart from that, there are various registers. A and B are the registers. It is defined in the question. A1 and A2 are the temporary registers for ALU. These are two marks. How they will behave, that's what we need to understand. Okay, so let's look at this. So consider the following data path as shown here. So this is your data path. Now apart from that, the register A, B, A1, A2, MDR and the bus and the ALU are 8-bit wide. So please try to understand all these things. What? Sir, this, all these things which I am representing in the blue color are 8-bit wide. What are the different things? So this is 8-bit wide, this is 8-bit wide, this is 8-bit wide, this is also 8-bit wide. Memory data register is also 8-bit wide, and this bus is also 8-bit wide. So when I say bus is 8-bit wide, what does it mean? See, this is the internal bus. If you want to transfer any data within the CPU, then that data will be transferred within by using this internal bus. If the width, or if this internal bus is 8-bit wide, then in one cycle you will be able to transfer only 8-bit of information. Clear? So when I say that this bus is of 8-bit, then you can eventually transfer only 8-bit of data using this bus in one clock cycle. Your ALU is also 8-bit wide. It means if two 8-bit operands are provided to this ALU, then your ALU will be able to perform the operation on 8-bit data. Okay. Apart from that, the mux, let's look at this. The stack pointer and the memory address register are 16-bit. So what does it represent? Sir, what stack pointer is used for what purpose? Sir, stack pointer is used to store the address of the top of the memory stack, right? Similarly, memory address register is also used to specify the address in our memory. So basically, if we are saying that memory address register and stack pointer are of 16-bit, then it means that the memory address will require 16-bit. So yeah, that's okay. That memory address register and stack pointer, they both are storing the memory addresses. Therefore, 16-bit information will be stored in these two registers. Otherwise, everything else in the CPU is capable of storing only 8-bit information, or they are capable of transferring 8-bit information. Now, please try to understand. The mux is of size 2:1. The mux is of size 2:1. Dmux is of size 1:2. Now, what does it mean 8 cross 2:1 and 8 cross 1:2? 8 cross 2:1 means there are 8 mux each of size 2:1. The Dmux is of size 8 cross 1:2 means there are 8 Dmux each of size 1:2. So you will provide 2 input, it will select 1 output. You will provide 1 input, it will select, it will enable 1 out of the 2 possible outputs. So that's the idea. Now please try to understand why this is being done. I'll explain in a while. So there are 8 mux of 2:1 size, that will 2 input will be given, 1 output, and similarly 8 Dmux of size 1:2. Each memory operation, okay, whenever you want to perform any memory operation, it takes 2 CPU clock cycle. Okay, see, it's an ambiguous statement. Most of the time, whatever if this statement is not given, then what will you assume? Sir, if this statement is not given, then first, in order to access the memory, first you will have to initialize the memory address register, and then based on memory address register, you will access the data from the memory into the MDR. So 2 cycles are required for that particular purpose, right? What this question is trying to specify, let's try to understand. Each memory operation takes 2 clock cycles, 2 CPU cycles, and uses memory address register and memory data register. So, okay. So each memory operation takes 2 CPU clock cycles, okay, and uses memory address register and memory data register. Now, please try to understand what does it mean that based on the memory address register, the address present in the memory address register, if you want to access the data and you want to transfer the data into the MDR, then 2 clock cycles are required. So what does it mean? Basically, I don't know whether you understand it or not, that based on the address present in the memory address register, based on the address present in the memory address register, if you access the memory and if you provide the particular data into the memory data register, then for this purpose 2 cycles are required. That is what is being specified in this particular question, right? So this operation itself will take 2 clock cycle. Generally, if it is not specified, we will assume that this operation can be completed in 1 clock cycle, right? Now, it's okay. So, and uses memory address register and memory data register. Apart from that, it is saying that stack pointer register can be decremented locally. Stack pointer register can be decremented locally. So, what's the idea? If you are trying to perform any memory operation based on the stack pointer, then after performing one push operation, you will decrement the value of stack pointer. Why? See, these are some things which you guys should understand. That generally when you implement a stack, then whenever you perform a push operation, you increment the value of top. Whenever you perform the push operation, you increment the value of top. But look at this, when memory is allocated to a particular process, then some space will be allocated for the code of that particular process, some space will be allocated for the data of that particular process. These are the static memory allocation. That means it will be it will not change throughout the execution of program, but some memory space is allocated to the process in the form of stack and heap. So this space will be utilized at the runtime. That means memory will be allocated and deallocated as and when needed from this area which is dynamically allocated to this particular process. So what happens? Stack grows in downward direction and heap grows in upward direction. So whenever you perform a push operation, the address will reduce. Whenever you perform a push operation, the address will reduce. Getting the idea? So if you keep performing the push operation, then the addresses will keep reducing. So generally, when the stack grows in the upward direction after performing a push operation, the value of top will be incremented. But when the stack is growing in the downward direction, then after performing the push operation, the value of top will be decremented. Therefore, if you are accessing the memory based on the stack pointer register, it means you are accessing the memory stack. Then if you are performing a push operation into that particular memory stack, then after that push operation, value of stack pointer will be decremented because the top will reduce after one push operation. Clear? So earlier, if top is pointing to this, then after one push operation, top will start pointing to this. So the value, the address will eventually reduce. Clear? Okay, so but what is being said, that stack pointer can be decremented locally. So if at all you want to decrement the value of stack pointer register, you don't need to. So what does it mean that it can be decremented locally? You don't need to use the ALU for purpose of decrementing the address which is present in the stack pointer register. You just pass the signal decrement to this stack pointer register, and the value of stack pointer, the content of stack pointer register can be decremented locally. Okay, that's it, right? Now please try to understand some more things. There is one instruction which is push R. There is one instruction push R. So you know that if it is a push instruction, then ultimately it will push something into the stack. It will push something into the stack. The value R is either available in processor in the register A or in B. We know that A or B are the registers. So registers A, B, A1, A2, whatsoever, right? So in this particular case, what is happening? There is an instruction which is push R. If you execute this push R, then R is actually nothing but either A or B. So R, the value of R is present either in this register A or B. But the implementation of this push R has the following specification. The implementation of this push R instruction has the following specification. What happens? Whenever you want to perform this push R operation, what will happen? Sir, the value of R will be pushed into the memory stack. Now, if you want to access the memory, then the memory cannot be accessed until you pass the address into the memory address register. But what's the actual idea? That the value of R will be pushed at the address the value of R will be pushed at the memory address which is available in the stack pointer register. Once you have pushed the value of R into the memory, you will decrement the value of stack pointer, so that if you want to perform the next push operation, then it can be performed at the current value of stack pointer register. So that's the logic, right? Now it is asking that how many CPU clock cycles are needed. How many CPU clock cycles are needed to execute this push R instruction? Sir, for you this may be two simple instructions, that okay, if you want to implement push R operation, then you will simply place the value of register A or B into the memory location at the address, into the memory at the address specified by the stack pointer register. But how actually the memory will be accessed? How actually the memory will be accessed? So please try to understand. If I want to perform this memory operation, that is content of memory location based on the address present in the stack pointer register will be divided by R. So please, whatever value is present in R, or basically A or B, that value needs to be stored in the memory. So please try to understand, if you want to transfer something, into the memory, then first of all that value should be present in the memory data register. So let me do it one by one. What will happen, sir? First of all, the value of A or B, whatever, A or B, it will be a single operation. The value of A or B needs to be transferred into the memory data register. Until the value is transferred into the memory data register, that particular data cannot be stored into the memory at any location. So this is the first thing which we will have to perform. So please try to understand, until and unless not specified, every micro operation can be, or micro instruction can be executed in one clock cycle. So it's a register to register transfer operation. It's a simple micro instruction. It can be executed in one clock cycle. Now, when the value is present in the memory data register, you need to access the memory. But in order to access the memory, that address must be passed to the memory address register. Now, please try to understand, that's the beauty of this question, that we need to transfer the address which is present in the stack pointer register into the memory address register, because the memory can be accessed only via memory address register. Now, the problem here is that stack pointer register is a 16-bit register and memory address register is also a 16-bit register. The bus is of only 8-bit. So whatever information you pass from stack pointer register into memory address register can be passed only with the help of this bus. This bus can carry only 8-bit of information in one clock cycle. So what you will have to do, sir, please try to understand. First, the content of stack pointer will be transferred to MAR, and in this particular cycle, that is, let me call it a cycle, it is a second cycle. In this particular cycle, the least significant 8-bit or most significant 8-bit, whichever you choose to transfer first, those 8 bits can be transferred from stack pointer register to memory address register. Now, for one more clock cycle, we will keep transferring the information from a stack pointer register to memory address register. In this second cycle, the remaining 8 bits will be transferred from stack pointer register into the memory address register. So in this, basically 8-bit will be transferred, and this next 8-bit will be transferred. I hope you understand, because in one clock cycle only 8-bit information can be transferred if the bus capacity is of 8-bit. Now that's the logic. I hope you understand that why this 8 mux of 2:1 are required. So the logic will be something like this. That both of them, it's a 2:1 mux actually. 2:1 mux. So what will happen, sir? In this particular mux, 2-bit information will go as an input. So please try to understand. There are 16 bits, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Now what will we do? Let me explain that, sir, this bit will go at the input 0 of this mux, and this bit 3, 4, 5, 6, 7, 8. This bit will go at the input 1 of this mux. Now what will happen when this value is 0? When this signal is 0, means in the first clock cycle, in the one cycle, we'll keep this value as 0. In the next cycle, we'll keep this value as 1. So when this value is 0, it will select the input at pin 0 and will produce as an output. So among these two bits, which one will be selected in when the input is 0 on this mux? Sir, when the input is 0, this least significant bit will be selected by this first mux. But sir, we need to select this 8 bits and we need to transfer this 8 bits using this particular bus. So basically there will be such 8 mux in parallel. There will be such 8 mux in parallel, each of size 2:1. Each of size 2:1. So the first bit will be provided to first mux, the next can be provided to, let me draw this so that you can understand, otherwise it is not important for that particular question. Now this second will be provided as an input to this second mux. The third one can be provided as an input to this third mux. Similarly, this will be provided as an input at the right hand side, and so on. So basically each one of this 8 mux will select the least significant 8 bits when the input or the select line is 0. When this select line is 1, each one of this 8 mux will select most significant 8 bits of this 16-bit stack pointer register. Clear? So that's why this is specified. I mean, I've just tried to explain that what is the meaning of why this 8 into 2:1 is written here, because there are 8 mux. In a mux you can provide multiple inputs, but each input will be of 1 bit. You can provide multiple inputs, but each input will be of 1 bit. So out of this 2 bits, one will be selected. Out of this 2 bit, one will be selected by some other mux. Out of this 2 bit, one will be selected by some other mux. So you need to select 8 at a time so that the output of 8 bit from this mux can be provided to the memory address register. Similarly, here also you will have 8 demux. To each demux will provide the input of 1 bit, and based on that, out of 2 possible outputs, one will be enabled and that corresponding value will be stored in the memory address register, right? So that's the basic idea, that in order to transfer the information from stack pointer register into MAR, because the size of the stack pointer register and MAR is 16-bit and the bus capacity is only 8-bit, therefore 2 cycles will be required. 2 cycles will be required. Got the idea? So these are the 2 cycles. Now what, sir? Finally, you also, please try to understand, you also need to decrement the value of stack pointer once this reaches here. But let me explain that particular thing. That okay, sir, these are the 3 cycles. After these 3 cycles, what will happen? MDR will hold the value of this R which needs to be pushed into the memory. MAR will hold the value at which the data needs to be pushed, right? So we are having this address in the MAR register, and the value which we want to store here, that R is also available in the MDR. So we'll simply perform the operation. Please look at this. We'll simply, in the 4th cycle, we'll try to transfer the data which is present in the memory at address MAR. Now you will say, sir, why MAR? We actually wanted to transfer the data at stack pointer register. No. Stack pointer, we actually wanted to transfer the information. Stack pointer, just 1 minute, respect me. Okay, I'll get back to you. So we actually wanted to transfer the information in the memory at the address which is present in the stack pointer, but we can never access the memory based on the stack pointer register. So whenever you want to access the memory based on any address, so when you access the instruction program counter, right, when you want to access the instruction based on the program counter register, then also first of all the address from the program counter register must be transferred into the memory address register. Then only that instruction can be fetched into the memory data register, and then from memory data register it will be transferred to instruction register. So these two are very important register for memory transfer operation. So The content of, I would write it on the other direction so that it will be easy for you to understand. Look at this. Sir, the content of memory location whose address is present in the memory address register will be updated by the content which is present in the memory data register. In the memory data register, the value of R is available. But please try to understand, this question is categorically saying this is one operation. If nothing is specified in the equation, then we will assume that this particular micro instruction can be executed in one clock cycle. But the problem here is that in the equation they have categorically mentioned that 2 CPU cycles, the memory operation will use 2 CPU cycles when it is accessing the memory based on the memory address register and memory data register. So 2 clock cycles will be required. So sir, in order to perform this operation, we will require 2 cycles 4 and 5. We will require 2 cycles 4 and 5. Now, no. After this 5 cycles, the value of R will eventually be available into the memory at the address which was present in the stack pointer register. Finally, you need to decrement the value of this stack pointer register. My question is, when you are performing this memory operation, you can simultaneously decrement. Why? Because to perform this decrement operation, you don't need anything else. You can directly produce these control signals which can decrement the value of stack pointer. So simultaneously, you can decrement the value of stack pointer and you can store it into the stack pointer. So for that, no extra cycle is required. Simultaneously, when one memory operation is being performed, simultaneously stack pointer value can be decremented. Yes, this stack pointer value can be decremented only after you have transferred this value of stack pointer into the memory address register. So this value stack pointer -1 or the decrementation of stack pointer value can be done in any of this 4th or 5th cycle along with this memory operation. So this is simultaneous, therefore no extra cycle is needed. I hope that's exactly same concept as we define with respect to program counter incrementation, that when we are accessing the memory, instruction from memory into the memory data register, simultaneously we can increment the value of program counter. The same thing is being done here, that stack pointer value can be decremented while we are performing the memory operation to push the value into the memory stack. Therefore, no extra cycle will be required for this decrement operation. So, sir, how many cycles will be needed? I hope you can understand that, sir, with respect to this particular operation, 5 cycles are needed. Come on. With respect to this particular operation, this 5 cycles are needed. Yes or no? And with respect to this particular instruction, no extra cycle is needed. When we are executing the first instruction in the last 2 cycles, we can decrement this value of stack pointer locally. Clear? So obviously 1 cycle will be needed for this, 2 cycles will be needed for stack pointer transfer, to transfer the value of stack pointer register into the MAR. Obviously 2 cycles because the bus is of 8-bit and the data is of 16-bit. Again, the memory operation will require 2 cycles, therefore 2 cycles will be consumed for this. So 2 cycles to transfer the data from stack pointer into the memory, 2 cycles to perform the memory operation, and 1 cycle to obviously load memory data register with the value which needs to be stored in the stack pointer. So overall 5 cycles are needed. So please guys, I mean, you guys may say, sir, one question, that much time. I am just trying to explain you the concept that whenever a question of this particular type comes, then what you need to do. Clear? Okay, so this is the first question. Let's try to understand the second question on the same concept. So consider the following data path of a CPU. So the data path is given whenever the memory address register will be used to place the address on the address lines of the system bus, and the memory data register will communicate with the data lines of the system bus. That's what we know, right? So MAR and MDR are used whenever you want to perform the operation on the memory device, right? Apart from that, for the internal communication, this internal bus will be used. For internal communication, this internal bus will be used. System bus is used for external communication. So whenever you are trying to perform a memory operation, the memory is connected externally. Therefore, system bus will be required, and to communicate with the memory device, memory address register and memory data register will be used. So this is just a data path which is given. Let's try to understand the ALU. Let's look at the question. The ALU, the bus and all the registers, the ALU, the bus and all the registers in the data path are of identical size. So there is no restriction on the size. All of them, whatever is present in this diagram, all of them are of same size, right? Apart from that, all operations including incrementation of the PC and general purpose registers are to be carried out in the ALU. So this was actually a common data question. I am not considering both the questions because the first one is quite easy. I am considering only one part of that question. So this particular thing, incrementation of PC, need not be present in this particular question. Why? Because in the second part of the question, it categorically says that assuming that PC is incremented during the fetch cycle of the password of the instruction. So we are assuming that okay, PC is automatically incremented when we were fetching the first word of the instruction. So we'll assume this because this is already given in the actual question, right? So generally, forget about that. Apart from this PC value, let's assume that all operations are carried out, all operations including this and incrementation of GPR, general purpose registers, are to be carried out in the ALU. So obviously, with respect to PC, generally we assume that PC value can be incremented locally. But in this particular question, in the first part, it was explaining that the incrementation of PC will also be carried out by the ALU. It cannot be carried out locally. But further, it goes and says that the incrementation of PC can be done while the first word is being fetched. Okay, so that's okay. 2 clock cycles. Look at this. This is different. In the previous question, when it was written that each memory operation takes 2 clock cycles and uses MAR and MDR, it is a different thing. In this particular question, when it is saying 2 clock cycles are needed for memory read operation, 2 clock cycles are needed for memory read operation. Look at this, how it is being specified. The first one for loading address into MAR. I hope you understand. Here, we were loading the address into MAR, and for that purpose itself we required 2 cycles. So it is a separate concept. Here it is saying that 2 cycles will be required. The first one for loading the address in the MAR. So in 1 clock cycle you will load the value at the address in the memory address register in the second clock cycle, and the next one for loading the data from memory into the MDR. So next one, when you say load the data from memory into the MDR, for this particular transfer only 1 cycle will be required. So 2 cycles are required, one to load the memory address register, one to transfer from memory into the data. So both of them can be carried out into 2 clock cycle. That is what is being specified in this new question. Now here the instruction call the subroutine and store the return address into RN. Call the subroutine and store the return address into the RN is a 2-word instruction. I am not going to discuss this particular instruction here. You don't need to worry about this in order to solve this question. So I'll not waste a lot of time because we have already utilized enough amount of time in the first question. So let's just try to understand that okay, something is being executed, and how do we execute this instruction is specified using register transfer interpretation. That if you want to execute this particular instruction, so the instruction call RN sub is a 2-word instruction. So it is given that it is a 2-word instruction, assuming that when we are fetching the first word of the instruction, the PC value is incremented. Obviously, if you have fetched only 1 word, that is a very common mistake which a student can commit in this particular question. When you are fetching the first word of the instruction, by what value the program counter value will be incremented? Whether it will be incremented by 1 or it will be incremented by 2. if the instruction size is of 2 words and if you have fetched only first word of the instruction, and if you are incrementing the PC value while you are fetching the first word of the instruction, by what value the program counter will be incremented? Sir, program counter value will be incremented only by the amount of data which you have fetched from the memory. So if you have fetched only one word from the memory, if you have fetched only first word of the instruction from the memory, then the program counter value will get incremented only by 1. Program counter value will get incremented only by 1. Its register transfer interpretation is that if you want to execute this, then once you have fetched this instruction, let's try to understand this. Sir, let's assume that this is your memory. This is your memory. And this is your instruction call RN subroutine. So two informations are available. I'm just going to explain that what actually the scenario is. In this first word, so this is your first word. This is your second word. In the first word, two information are available. What is the instruction and the information about the register in which the return address needs to be stored is also available in the first word. In the second word, the subroutine, the address of the subroutine to which you are, the subroutine which is being called, the address of that subroutine is available in the second word. Let's assume that the address of the first word is 100. Let's assume that the address of the first word is 100 and the address of the next word will obviously be 101. And this is the address of next instruction. Here we have the next instruction in the sequence. Here we have the next instruction in the sequence. Now, so what will be the address of the next instruction? The address of the next instruction will be 102. Address of the next instruction will be 102 if the instruction is available at address 100. Now my question is, while if it is a subroutine call instruction, then after the execution of this instruction, what will happen? Program counter will get loaded by the subroutine, the address of the subroutine. Program counter will be loaded by the address of the subroutine. And when you return from subroutine, you need to return to the next instruction in the sequence. Therefore, this return address 102 will be stored somewhere in the system so that when you return from the subroutine, you can transfer the control to this particular instruction. Clear? So that's the logic. So let's try to understand this. That when we have fetched this first instruction, after fetching this first instruction, after fetching this first word, what value will be available in the program counter? So the value that will be available in the program counter after fetching the first word will be 102. Now, when we start executing this instruction, what will happen? So when we start executing this instruction, it will tell us to add 1 into the current value of program counter, and then it will want us to store that incremented value into the RN. Please tell me, are we incrementing the value of program counter? No, sir. We are not incrementing the value of program counter. We are just adding 1 into the current value of program counter and we are storing it into RN. So please look at this particular diagram. If I want to increment the value of, if I want to perform PC plus 1, and I want to store it into register RN, then how will I do it? Sir, in order to execute this instruction, first of all, I will have to transfer the value of program counter into one of this temporary register S or T, because if you want to increment the value, if you want to add something, then those addition operation can be performed only using the ALU. It is already given, right? So all operations needs to be performed by the ALU. So if ALU is performing the operation, then ALU can perform operation only when the operands are available in this temporary register. So the value of program counter will be loaded into the S. Then you will simply add S plus 1 you will simply add S plus 1 and the output can directly be stored into register RR. The output can directly be stored in the register Rn. So this two micro instruction can add 1 into the current value of program counter. This two micro instruction can add 1 into the current value of program counter and can store that result into this register Rn. So this is done. This is done. Now what? Sir, PC will be incremented. Then what? Sir, the memory will be accessed based on the address which is present in the program counter. The memory will be addressed. Please try to understand. I did not increment the value of program counter. I just added 1 into the current value of program counter, that is the value becomes 102 and we have stored 102 into Rn. We have stored 102 into Rn and because of that the return address is available into the register Rn. Return address is available into register Rn. The address of subroutine is available at the address which is present in the program counter. So we need to fetch this address from this memory address and we need to store this address into the program counter. Right? So that's the logic. That's what is being done. That we need to access the memory based on the address which is present in the program counter, and on that address whatever value is available, that value needs to be loaded in the program counter so that the program counter can be initialized with the first address of the subroutine. First address of the subroutine. So for that purpose, what will you do? Sir, if you want to perform this, let's go there and try to understand. That sir, if I want to access the memory based on the address which is present in the program counter, and if we want to transfer it into the program counter register, then how will we do it? Sir, in order to access the memory, first of all the address which is present in the program counter must be transferred into memory address register, otherwise the memory cannot be accessed. Once you have initialized, once you have loaded the address into the memory, you can simply perform the memory read operation. What, sir? Content of memory location which is present in the memory address register will be first come into the memory data register. So after this two micro instruction, the content of memory location whose address is present in the program counter register will come into the MDR, but we actually need to transfer that address into the program counter register. Therefore, the content of MDR will be transferred into the program counter register. So these two micro instructions will execute the first instruction. This two micro instruction will execute the first register transfer instruction of this particular instruction, and this three micro instruction will execute this second register transfer instruction corresponding to this particular instruction. Getting the idea? So in order to execute this particular instruction, these two things needs to be done. For executing this, two cycles are required. One, to transfer the value from program counter into the temporary register S. Then second, to add 1 into the value which is present in the temporary register and to store it into the Rn. So for this particular purpose, 2 cycles are required. For this, 3 cycles are required. Why 3 cycles are required? So in the very first cycle, the value of program counter will be transferred to MAR. Then based on the address which is present in the MAR, memory will be accessed and the value present at that address will be transferred into the MDR, and in the third cycle the data will be transferred, or the address will be transferred from MDR into the program counter. Finally, the address must be present in the program counter, right? So 3 plus 2, how many cycles are needed? Sir, 5 cycles are needed. Sir, 5 cycles are needed for this particular thing also. Okay, sir. Next, let's look at this particular question. This is also related to same concept. The data path shown in the figure computes the number of ones. Okay, let's look at this. The data path, there is a data path. This is a data path. This does what, sir? It actually computes the number of ones. It actually computes the number of ones in 32-bit input word. It just computes the number of ones in 32-bit input word, where exactly the 32-bit input word is available corresponding to an unsigned even integer stored in the shift register. So that 32-bit input word is definitely an unsigned even integer? Please try to understand. If a 32-bit word is an unsigned even integer, so if it is unsigned, then its most significant bit may be 1 or 0. It doesn't matter because it is unsigned. But if it is an even number, then is it guaranteed that the least significant bit will be 0? If a 32-bit number is an even number, then it is guaranteed that the least significant bit of that particular number will be 0. So in this 32-bit input word, which is representing an unsigned even integer, cannot have more than 31 ones into it, can never have more than 31 ones into it, because one of those 32-bit is guaranteed to be 0 because it is even. Now that 32-bit word is actually present in the shift register. So this is actually the register which is holding, that 32-bit input word. So 32 means 0 to 31. So this 32-bit input is present into this shift register. The unsigned counter, so there's a counter, there is also an unsigned counter, it's okay. Initially 0, so initially the value of this counter is 0, is incremented. So this particular counter will get incremented if the most significant bit of the shift register is 1. So whenever this most significant bit is 1, this particular counter will be incremented. If this most significant bit is 0, it will not get incremented. Now it's okay, it's simple. Please try to understand. Sir, this shift left will be permanently 1. So that one by one all the bits of this shift register will keep shifting into this counter. If this 1 is shifting into the counter, then counter value will get incremented. If 0 is shifting into the counter, then the counter value will not get incremented. Yes or no? So we will keep shifting the content of the shift register. If 1 is shifted into this counter, then the counter value get incremented. If 0 gets shifted, then the counter value remains same. Now, can you reset the counter value in between? No, sir. Please try to understand. Until we are done with the process, we cannot reset the counter value. So this reset pin has to be 0 until the complete computation. When will you exactly load the output? So, when will you load the output? Sir, we will load the output when this complete process becomes 0. So, during process it will be 0. It will be 0 during process, right? This will be 1 initially. Why? Because when you start counting, when you start the process of counting, the value of count should be 0. When you start the process of counting, the value of count should be 0. Therefore, initially it will be 1 so that the counter value becomes 0. Then afterward it will remain 0. Afterwards it will remain 0 so that the counter value does not become 0 in between, that is in between when we are still in the process of counting, right? Now, the output will not get loaded, so it will be 0 during the process and it will become 1. It will become 1 in the end. When the process of counting is complete, counting is complete, it should become AND. Now please try to read the question. That's what, I mean, the general intuition is that I was actually trying to count the number of ones into this 32-bit register. So by looking at this diagram, this are the things which we can observe. Let's look at this. The microprogram for the control. So this is a control circuit. Now the microprogram for this control circuit is as shown in the table. So in this table you will say that begin and end. So you will begin the process of counting the number of ones, you end the process of counting the number of ones. Now in the table below with the missing control words. So these are the missing control words. We don't know what these words are. Now what is being asked, sir? The very first question, what is being asked, that the counter width. Sir, it is a k-bit counter. Do you know that the value of the number of ones cannot be more than 31 because one out of them is guaranteed to be 0. One of them is guaranteed to be 0. It's a 32-bit input. It's a 32-bit input. But the number of ones into this 32-bit input can never be 32. It will be 31. Now, if you want to count between 0 to 31, k bit will be equals to 0 to count between 0 to 31. Sorry, k bit value will be 5. The value of k has to be 5 if the number of ones are going to be between 0 to 31. So the value of this k bit counter or the width of this counter will be 5 bit. So using 5 bit counter, you can count the 32 different values from 0 to 31. So it's okay from 0 to 31, right? So that's fine. The maximum number of ones can be 31. The maximum number of ones can be 31. So it is able to represent 31 also. Using 5 bit, you can represent 31 also. So that's the first answer. So the value of k will be 5. The value of k will be 5. The number of missing micro instructions, please try to understand. It is saying that how many missing micro instructions will be there. How many times? So please try to understand. Initially, when you begin, you will reset the counter. Initially, when the process is just about to begin, the shift left will be 0 and the load output will be 0. Then what will you do? Sir, reset counter needs to be 0 during the process. I told you that reset counter must be 0 when you are in the counting process. Yes or no? And this shift left should always be 1 because one by one all the bits should be shifted towards left so that the counter value will get incremented whenever the most significant bit is 1. Right? Now this load output will not be loaded. Load output will not be loaded until the process of counting becomes complete. Yes or no? So the value of reset counter pin should be 0 during the process of counting. The value of shift left should be 1 and the value of load output should be 0. So basically this control word for missing micro instruction must be, the control word must be 0, 1, 0 for all this micro instruction. This micro instruction 1, this micro instruction 2. I don't know how many micro instructions will be there, but for all this micro instructions, the control word should be 0, 1, 0. Control word represent the control signal. So reset counter control signal should be 0, shift left counter control signal should be 1 and load output control signal should be 0, right? Now finally when we are done with the process of counting, we will not reset the counter until we want to start the next counting. We will not reset the counter until we want to start the next counting. We will stop the process of shifting left side. We will stop the process of left shifting and we will load the output because once the process of counting is complete, we will load the output. Now what is the next thing that is being asked? Missing micro instruction. How many times we need to generate this control words? How many times we need to generate this control words? So please try to understand. To answer, so the value is either 32 or 31. The value is either 32 or 31. But my question is that sir, if the number of ones cannot be more than 31, then why do you need to shift all these 32 bits? Why do you need to shift all these 32 bits? If you know that this is an even integer, then you need to shift only 31 times. You need to shift only 31 times. So the value of n will be 31 in this case. Value of n will be 31. So sir, the value of k has to be 5. The value of n has to be 31 and the control word will be 0. So 5, 31 and 0, 1, 0. 5, 31, 0, 1, 0. 5, 31, 32. So 5, 31, 0, 1, 0. The k bit counter, because the number of ones can be up to 31. So to count up to 31, k value should be 5. The number of missing micro instructions should be 31. I mean the 32 is also a right answer. 32 is also a right answer, but this will be a redundant instruction. Why do you need 32 when you are sure that the number of ones will not be more than 31? Number of ones cannot be more than 31. Then why are you shifting that last least significant bit towards left when you know it is anyway going to be 0, right? So apart from that, control word will be 0, 1, 0, that is in between. You cannot reset the counter. You should always shift towards left and the load output will be 0 in between. The load output will become 1 at the end. Load output will become 1 at the end. So this will become 1 at the end. This will be 1 during the process. At the end it will become 0 and it will remain 0 until the process of counting starts for the next time. Clear? So that's the answer. Option D is the correct answer. Let's look at the last question. So these are the most important 5 questions. Let's look at this 4th question. Consider a CPU where all instruction requires 7 clock cycles. Please try to understand. Generally, in order to solve this type of question, what will we require? That each instruction requires how many micro instruction? We assume that each micro instruction can be executed in 1 clock cycle. But in this particular question, something else is given. So consider a CPU where all the instruction requires 7 clock cycles to complete the execution. All the instructions. So each instruction requires 7 clock cycles. There are 140 instructions. So please try to understand. Number of instructions supported by the processor 140. So this instruction I1, this instruction I2, this instruction I3. So there are 140 instructions. Wow. There are 140 instructions. Please look at this control memory we are talking about, right? So generally we store the microprograms of all the instructions in the control memory. In microprogram, what will be there? Sir, in microprogram there will be micro instruction, but we don't know how many micro instructions are there in the microprogram of each instruction. We don't know how many micro instructions are there in the microprogram of each instruction, but this information is available in some other form. So it is given that all instruction requires 7 clock cycles. So one micro instruction is generally executed in 1 clock cycle. Therefore each instruction will require 7 micro instructions. So there will be 7 micro instructions, micro instruction 1 to micro instruction 7 with respect to instruction 1, micro instruction 1 with respect to instruction 3 to micro instruction 7 with respect to 3, and so on. So what is the total or total size of control memory? Total size of control memory in micro instruction, that is overall, or in micro instruction or in control word? In micro instruction or control word? Sir, overall 140 microprograms will be there. Overall 140 for each instruction the microprogram will be present in the control memory. So overall 140 microprograms will be there, and for each microprogram there will be 7 micro instruction. For each program there will be 7 micro instruction. I don't know. So there are 140 instructions in the instruction set. So for each instruction you will have a microprogram. It is found that 125 control signals are needed. Oh, so I have just passed some information a little bit early, that why have I counted this control memory size, because I knew the question. So I believe that this was a little early for you guys. You guys must be thinking that why are you doing this? So I'm sorry, right? So please try to understand that there are 7 clock cycles required for the execution of each instruction. Overall there are this 140 instructions supported by the processor. It's okay. It is found that 125 control signals are needed to be generated by the control unit. So number of control signals needed in the system. This is known. Number of control signals in the system are given as 125. Good enough, sir. Right? Now, while designing the horizontal microprogram control unit, so when you design a horizontal microprogram control unit, what do? Whether it is horizontal or vertical, the only aspect is that you need to store the microprograms of all the instructions in the control memory. If it is horizontal, then the control word size will be different. If it is vertical, then control word size will be different. But ultimately, you need to store the microprograms of all the instructions in the control memory. So sir, if there are 140 instructions and the microprogram of each instruction requires 7 micro instructions, so overall how many micro instructions will be there in the control memory? Sir, overall number of micro instructions will be there, there in the control memory will be 0, 8, 9. Sir, total 980 micro instructions are there in the control memory. Okay, sir. So total number of micro instructions in the control memory are 980. Now, apart from that, what is given? Single address field format. Please, I don't know how many of you know this concept that when we define the control word. So what is the format of control word? Sir, format of control word is there are some branch condition. Oh, don't confuse branch condition, then flag info, then there will be control field, and generally we have one address field. Generally we have one address field. Sir, when exactly this address field is used? Sir, in single address field means there will be only one address field. What will be the logic? Sir, whenever branch condition is true, whenever branch is taken, the next micro instruction will be fetched from this particular address, otherwise you will fetch in the sequence. Sir, you may also have two address field format. So in two address field format there will be two addresses. In two address field format there will be two addresses. What will happen? When the branch is taken, one address will be used. When branch is not taken, then another address will be used. But the situation is, when branch is not taken, why do you need to store the address into the micro instruction? You can simply increment the current value, or you can simply increment the address or the current address in the control memory, so that you will get the address of the next micro instruction. So you don't need to store this. So generally we don't use two address field format. Generally we don't use two address field format. It is just, this statement is given just to confuse that what is this. You may think that something new is given. No, it is nothing new. If you don't bother too much about this word, then your answer will be correct, right? So that's the idea. Single address field format is in which there is only one address field in the control word. Please try to understand. Please try to understand. This branch field and flag fields are used only if the information about them are given. Otherwise, these two fields are optional. But this two field, control field and address field, are mandatory. They must be present in every control word. Now, sir, if it is horizontal microprogram control unit, then how many bits will be present in the control field? Sir, if it is horizontal microprogram control unit, then the number of bits will be same as the number of control signals. Yes or no? Number of bits will be same as number of control signals. How many control signals are there? So there are 125 control signals. Now the next thing is, so this overall field will become the control word. So we know how many bits will be required. For the control field. But how many bits will be required for the address field? How many bits will be required for address field? Sir, this address field is used to specify every micro instruction. So please try to understand. There are 980 micro instruction in control memory. Therefore, number of bits in address field. How many bits will be there in the address field? Will be log of base 2 of 980 ceiling function. Sir, how many? So this value will be 10. The 10 bits will be required in the address field to address each of the micro instruction in the control memory. So this value will be 10. So 125 bits will be there in the control field with respect to horizontal microprogram control word, and 10 bits will be there in the address field with respect to horizontally microprogram control word. If nothing is given about the branch and flag, then we will assume that no bits are required for them. Now, what is the minimum size of control word and control address register? Sir, in control address register, please try to understand what do we store in the control address register? So the control address register will be used to store the memory address or control memory address. So what does it store? Used to store the address of micro instruction. Therefore, how many bits? 10 bit. What is the size of each? What is the how many bits are present in the address of? How many bits are required to represent one micro instruction in the control memory? So 10 bits are required to represent one micro instruction in the control memory. Therefore, just like memory address register is used to access the memory, control address register is used to store the control memory. In memory address register, we store the address of our memory cell. So in control address register, we will store the address of our control memory. Now the address of our control memory is of 10 bit. Therefore, control address register is also of 10 bit. So the answer for this will be of 10 bit. And what is the minimum size of the control word? So the minimum size of the control word will be 125 plus 10. Minimum size of the control word will be 125 plus 10, that is 135. Minimum those many bits are required. Apart from that, if branch field and fact field are also present, then some extra bits will also be there. But minimum this true fields will be present in every control word. Therefore, minimum 135 bits are required. So 135 for the control word size and 10 bits for the control address register size. 10 bits for control address register size. So this is again the answer, option D, 135 bits of control for control word and 10 bits for the control address register. So these are the different questions related to the concept of ALU, data path and control unit. The questions are damn easy. I've just taken that much amount of time so that you can understand each and everything, that how should you actually try to interpret the question, what are the things which should be learned from a particular question. That will be all. Tomorrow's topic will be very important, because tomorrow we are going to discuss one of the most important topic of computer organization and architecture, that is instruction pipeline. So in tomorrow's session, we will discuss some of the good quality questions of the topic instruction pipeline. And I mean, every year at least one question will be there from instruction pipeline, and at least one question will be there from memory organization. So 4 marks are guaranteed from these two particular topics of COA. One is instruction pipeline, 2 marks are guaranteed. 2 marks are guaranteed from memory organization. Apart from that, 2 extra marks will be there from one of these two topics. Ultimately 5 to 6 marks question will be there from instruction pipeline and memory organization. So these two are very important. So tomorrow at the same time, that is at 7:30 p.m, we are going to discuss the concept of instruction pipeline. So mark your calendar for tomorrow's session. This is the Telegram group. If you guys have any doubt, you can post your doubts at this particular group. I'll be happy to answer. So this is it for this particular session. Thank you very much. If you liked the video, then please hit the like button. If you are new to the channel, then subscribe for the channel and press the bell icon to get the notification about our upcoming videos. That will be all. Thank you very much. Happy Dussehra once again. Enjoy the festival. Stay safe.